Yeah, why still people are not joined? Is there any reason? Yes, Akshay Kumar, can you just summarize what we have discussed in the last class?
Yes, sir.
Yeah.
We started with differential encoding,
Ah,
the operation of differential encoding, like how it takes XOR operation and
it is
works.
XOR or XNOR operation?
Sir,
It is XOR or XNOR operation?
XNOR.
XNOR, okay.
And then we studied about regenerative repeater circuit.
Okay.
The we discussed about the functions and performance of each block. It
Yeah.
is made of the distorted PCM wave is given to amplifier or equalizer,
Ah,
where it is amplified, and equalizer removes the amplitude and phase distortion.
yeah.
This wave is given the output is given to decision making wave,
The-
and again the output is taken for timing circuit where
Yeah.
rectangular pulses, train of pulses are generated, and even that is given to the output is given to decision making device.
Okay.
It is basic decision making device is basically a comparator circuit which
Okay.
compares the values output values of both the blocks, and if amplifier circuits output value is greater than timing circuit, it provides amplitude of 1. If timing circuit value is great, output value is greater, it provides an amplitude of 0, and thus the PCM wave is regenerated in the output.
Okay.
And we also studied about filtering, sir.
Okay.
Decoding and filtering.
Yeah, that is a receiver of PCM.
Yes, sir.
Okay, fine. Thank you. Okay, still only few people are there. Is there any reason? See, 6 minutes gone. Only I'm finding, including me, it is 13. Okay, do one thing. I will dictate problem. You can note down. Start solving that. Okay. It is very interesting. And yeah, shall I dictate?
Yes, sir.
Ah. A CD recording system. CD means your compact disc. Okay. A compact disc recording system samples each of two stereo signals. I repeat once again. A CD recording system samples each of two stereo signals with a 16-bit analog to digital converter with a 16-bit analog to digital converter at 44.1 kbps. At 44.1 kbps. First one, determine determine the output signal to quantizing noise ratio. Determine the output signal to quantizing noise ratio for a full scale sinusoid. For a full scale sinusoid. Second one, the bit stream of digitized data The bit stream of digitized data is augmented by the addition of error correcting bits, comma, clock extraction bits, and display and control bit fields. I repeat once again. Second one, the bit stream of digitized data is augmented by the addition of error correcting bits, comma, clock extraction bits, and display and control bit fields. These additional bits represent these additional bits represent 100% overhead. These additional bits represent 100% overhead. Determine the output bit rate of the CD recording system. Determine the output bit rate of the CD recording system. Yeah, third one. In that first one I said determine the output signal to quantizing noise ratio for a full scale sinusoid. Second I would dictated. Third point in that the CD can record an hour's worth of music. The CD can record an hour's worth of music. Determine the number of bits recorded on a CD. Determine the number of bits recorded on a CD. The next point, for a comparison, a high grade collegiate dictionary, may contain 1500 pages. A high grade collegiate dictionary may contain 1500 pages, comma, 2 columns per page, comma, 100 lines per column, comma, 8 words per line, comma, 6 letters per word, comma, and 7 bits per letter, on average. 7 bits per letter on average. Please stop. Determine the number of bits required. Determine the number of bits required to describe the dictionary. Determine the number of bits required to describe the dictionary. And estimate the number of comparable books. That can be stored on a CD. And estimate the number of comparable books that can be stored on a CD. Hope everybody has noted, whoever was there from the beginning. So I said it is very interesting and application oriented problem. Really, if you have understood the concept of PCM, definitely you will be able to apply your thoughts and you will be able to solve this problem. If you have any doubts, you can ask. If you want, I can repeat once again. Okay, for cross verification, if at all you want to verify your data, what you have noted, I can read it once again. Yes, is it noted? Everybody, whoever was there from the beginning. Yes, I'm asking you people only. Please respond whether you could note down or you have not noted or you want me to repeat once again. I can repeat. Hello?
Done, sir.
Done. Noted, na?
Yes, sir.
Yeah. Yes, what about others? Sachin is saying he has noted well. What about others? Kuber, have you noted, man? Kuber, he is out of place, I think. Leah, yes, Leah. What about Hima? Hima, no response. Neeraj, yes,
Yes, sir.
Neeraj. Have you noted
I'm
problem?
writing it down, sir.
Sir, I joined a little bit late, so I'll just copy it some.
From whom you will copy? You want me to repeat? I will repeat.
Sir, is it a lengthy question?
Yeah, a little bit lengthy, but interesting application oriented, as I said. I will
Uh,
repeat. Whom you will ask? Huh?
so someone was written it. I think Kuber or someone.
He is not responding only now.
There, sir, I'm there. It's a
There.
network.
Okay. Okay. Fine. Yes. What about Leah? So I think I don't. You people don't want me to repeat this question. Yeah, anybody has solved? May I know the answer? Hello? Yes, Sachin started solving.
I'm doing so.
Uh, what about Kuber, Akshay?
Doing,
So
sir.
visualize. You're searching or doing it on your own? Kuber? Yes, Vishal has joined now. So I will not be doing what is the problem. I've given. Right?
Sir, I'm copying the question, sir.
Okay, good. You people are communicating with each other. Yes, what about Noreen?
Yes, sir, I'm trying to solve it.
Are you solving the problem?
Yes, sir.
Yes, what Sagar? You are joined now. Yes, Shreyas.
Sir,
ಏನು ಪ್ರಾಬ್ಲಮ್ ಮಾಡ್ತಾ ಇದೆಯಾ ಅಥವಾ ಇಲ್ವಾ ಯಾವ ಜಾಯ್ನ್ ಆಗ್ತೀಯಾ ಬಿಡ್ತಿದ್ಯಾ
sir,
ಸಿ
question
ಹೌ
ಕೇಳ್ತೀವಿ.
ಪೀಪಲ್ ಆರ್ ಜಾಯ್ನಿಂಗ್
Copying question, sir.
ಕಾಪಿಂಗ್ ಕ್ವಶನ್ ಸೊ ಯುವರ್ ಫ್ರೆಂಡ್ಸ್ ಹ್ಯಾವ್ ಶೇರ್ಡ್ ಯು ಪೀಪಲ್
Yes, sir.
ಎಸ್ ವಾಟ್ ಮಾ ಗಾಯತ್ರಿ ಯು ಆರ್ ಜಾಯ್ನಿಂಗ್ ನೌ
Sir, I
ಗಾಯತ್ರಿ
had internet issues, sir. That's why I didn't join.
ವಾಟ್ ಸಾಗರ್
Yes, sir.
ವಾಟ್ ಯು ಆಲ್ಸೋ ಜಾಯ್ನ್ ವೆರಿ ಲೇಟ್
So internet problem. So I was too slow. I couldn't join.
at least are you solving the problem you
Yes,
taken
I'll
from your
take it
friends
from. Yes, I'll take
Oh,
it from them and solve it now.
okay yes, what about Chandana
Yes, sir.
you joined at right time you have a problem with you
Yes, sir, I have question.
okay yes Ananta
Sir, I took
Ananta
question, sir. I'm solving, sir.
solving Aditi yes Aditi
Yes, sir, I'm solving.
solving okay yes Manasa Arya Manasa SH
Yes, sir. I'm
are you
solving.
solving okay yes Leah what about Karunya
Yes, sir, I'm solving.
are you solving no problem
Yes, sir.
okay what happened to Leah she is not responding Yes, how many of you have understood the problem? Is it really interesting or not? I may ask this type of problem for your internals. Yes, Skanda.
ಸರ್ ಟ್ರೈ ಮಾಡ್ತಾ ಇದೀನಿ ಸರ್ ಸಾಲ್ವ್ ಮಾಡಕ್ಕೆ.
Yes, is it possible to share your answers at least for first one? What is the first question? Need to determine output signal to quantizing noise ratio. Yes, anyone can say what is the formula you are using? Output signal to quantizing noise ratio. Yes, Manasarya, can you tell what is the equation you are supposed to use for finding this? Manasa. Yes, Manasarya. What about Gayatri? Can you tell? Gayatri.
Sir?
What is the formula you're going to use for finding the first one? Output signal to quantizing noise ratio. Do you have any idea? No idea. Yes, Shreyas. Shreyas.
Sir,
What is the formula you're supposed to use, man, for finding output signal to quantizing noise ratio? I remember what formulas we have discussed today. Output signal to quantizing noise ratio. Yes, in terms of dB, what is the expression, man? Output signal to quantizing noise ratio is 1.8 plus a 6R, right? 1.8
yes, sir.
plus 6R. There is a 6 dB rule. Here, what is the value of R in the given problem? So, what is the value of R? How many bit ADC it is?
16.
16-bit ADC means the value of R will be 16. So 1.8 plus 6 into R, that will give you the value of output signal to quantizing noise ratio in terms of dB. Okay, so that is the solution for the first one. Hope how much it is getting?
97.8, sir.
Yeah. Okay, that is the dB. Yeah, what about the second one? We need to determine the output bitrate of the CD recording system. Right? It says the bit stream of digitized data is augmented by the addition of error correcting bits, clock extraction bits, display and control bit fields. These additional bits represent 100% overhead. So we need to determine the output bitrate of the CD recording system. And what is given in the problem? He has given 16-bit ADC at 44.1 kbps. Right? So that is the bitrate. So we need to find out the input bitrate first. So input bitrate will be 2 times, right, that whatever the data rate is given, that is 44.1 kbps. So 2 into 44.1 into 10 power 3 into how many bit ADC it is? 16-bit ADC. So into 16. If you do, you will come to know what is the input bit rate. So how much it is roughly? Anybody can say? So it is in 16-bit ADC. He has said it is 44.1 kbps is the data rate, right? So input bit rate will be twice of that. So 2 times 44.1 kbps into 16. How much you will get? Yes, multiply and if people can tell, na? 2 into 44.1 into 10 power 3 into 16.
1411200.
Yeah, 1411 Mbps it is. Can I say is it Mbps? Megabits per second.
1.411 mega bit.
1.411 Mbps. Okay. So for that, we need to add 100% overhead. Right? He said no, whatever that error correcting bits, clock extraction bits, display and control bits, right? So 100% means it will be again 1.411 MB. Means 2 times of that. That will give you the total input bit rate. So 2 into 1.411 Mbps, which is equal to how much you will get? 2.822 Mbps, right? So that will be the input bit rate for that recording. That is the output bit rate of the CD recording system. Okay. Hope I am clear. Yes, is that clear? The output bit rate of the CD recording system will be 2.822 Mbps. Okay, I said input bit rate will be 1.411 Mbps, right? Which includes 100% overhead. So the output bit rate will be 2 times of that. That will give you 2.822 Mbps. Then what is the third one? He says the CD can record an hour's worth of music. Okay. So you need to determine the number of bits recorded on CD. So now we know what is the output bit rate of the CD, right? So how much it is? 2.822 Mbps. Means 2.822 megabits per second. Okay. So he is asking it can be recorded for a hour's worth of music. So 1 hour means how many seconds it will be? 3600 seconds, right? So you can multiply that. That is what? 2.822 Mbps, right? Into 3600. That will give you the number of bits recorded on the CD. Hope I am clear. See, we are able to record 2.822 Mbps, right? Means 2.822 megabits per second. He said CD can record an hour's worth of music. So 1 hour means 3600. So 3600 into 2.822 MB. So that will give how much? 2.822 into 10 power 6 into 3600. Yes, which is equal to how much you will get? Yes, anyone can say what is the multiplication of that? 2.822 into 10 power 6 into 3600. Yes, Ananta, can you multiply and say?
Yes, sir. Yes, sir.
How much you will get, man? 2.822 into 10 power 6 into 3600, I'm saying. Yes, is it calculator exceeding digits? Ananta? I hope it will be around 10.16 gigabits. Means 10.16 into 10 power 9.
Yes, sir. Yes, sir. Yes, sir.
So in an hour, you will be able to record so many bits of data. Okay. So what is the last one? He is comparing that with, he is asking us to compare with number of books. He has told what a high grade collegiate dictionary may contain 1500 pages, 2 columns per page, he says, then 100 lines per column, then 8 words per line, okay, 6 letters per word, and 7 bits per letter on average, right? So with that, is asking us to find out the number of bits required to describe the dictionary. And is asking to estimate the number of comparable books that can be stored on CD. Yeah. What will be your answers? See, 1500 pages. Each page has 2 columns, right? So just you have to keep multiplying all those numbers, if I am correct. 1500 into 2 columns per page, right? Then each column will have 100 lines. So 1500 into 2 into 100. Then 8 words per line. Into 8 you can make. Then 6 letters per word. Into 6 you can make. Then 7 bits per letter. Into 7. So 1500 into 2 into 100 into 8 into 6 into 7. That will give you how much? Yes, how much it will be? That is the number of bits required to describe the dictionary. Yes, you people can't multiply and say how much you will get. 1500 into 2 into 100 into 8 into 6 into 7. Is it 100.8 into 10 power 6 bits? That's
Yes,
what I
sir.
mean to say is 100.8 MB. Okay, 100.8 MB. Then he is asking us to compare with number of books, right? So that is the number of bits required to describe the dictionary, right? So including 100% overhead, already we found what is the number of bits recorded on CD. That is what? 10.16 GB. Right? So we need to divide that 10.16 GB divided by this one, 2 times 100.8 MB. Why it is 2 times 100.8 MB? Because of additional 100% overhead. Okay. So if you do that, how much you will get? 10.16 GB divided by 2 times 100.8 MB. I think it will be roughly around how much? Yes, you can't divide 10.16 GB divided by 2 times 100.8 MB. Yes, somebody can say, na, what is the number you get? 10.16 GB is the total number of bits recorded on CD, right? And
Sir, TB, no, sir. 10.16
GB. Huh? GB means it is 10 power 9 gigabits. It is 10.16 GB is the number of bits recorded on CD. Then number of bits required to describe the dictionary is 100.8 MB. Okay, with 100% overhead, I can take it as 2 times of that, right? So to find out how many books I can compare,
50.396.
So 50 point something, right? So we can round off to 50. So we can say that CD contains equivalent of about around 50 books. Okay. So this is a very good example what I can say to understand the concept of this analog to digital converter. Okay, this type of real-time examples creating itself is a great challenge, isn't it? Yes or no?
Yes,
I
sir.
don't know how many of you could understand, could think about this. Okay, similar to that, we will solve some more problem. I think I will now take up the theory about a digital, that is a delta modulation. That is, then I will come back to the problems. Okay. Hope you're able to see now. Hope you're able to see my slide.
Yes, sir.
Yeah. So far we have discussed about PCM, right? Pulse code modulation. The drawback of PCM is it requires more bandwidth as the number of bits used to represent increases, means as the number of quantization level increases, so we need more bandwidth. So to overcome that problem, we go for another analog to digital converter is known as delta modulation. Okay. So here what is done is, in case of delta modulation, the incoming message signal will be oversampled. Okay. So we all know what is oversampling. So it will be slightly higher than the Nyquist rate. Okay. The signal will be sampled much higher rate than the Nyquist rate, right? So why it is done so? It is done to increase the correlation between the adjacent samples. Okay. To increase the correlation between the adjacent samples of the signal, the incoming signal will be sampled at much higher rate than the Nyquist rate. Okay. So why it is done so? It is done so to use the simple quantizing strategy for constructing the encoded signal. Means we are aiming at reducing the bandwidth, right? So how do we reduce the bandwidth? We need to reduce the number of bits used to represent the number of quantization levels, right? So for that we are doing all this. Okay. So the incoming, in case of delta modulation, the incoming the message signal will be oversampled. Okay. which is done to increase the correlation between the adjacent samples of the signal. Okay, so that is done to use the simple quantizing strategy for constructing the encoded signal. So this delta modulation also provides the staircase approximation of the oversampled version of the message signal. So here also we get a staircase version of the signal. Okay. So this you will understand if I go with the example. Okay, just if I say theory, you may not be. So I will take the example and I will explain you this. Yeah, this is what the example is. So now you don't look at the equations. Let us try to understand with this example. Okay, see this dashed line is my message signal. Okay, incoming message signal, that is M of T. Okay, dashed signal, and this staircase signal is there. That is my staircase approximation signal. Okay, means how do I represent this staircase is with this binary data. Okay, so this is my binary sequence of the output of delta modulator. Okay, so let me just explain how do we get this. So here what we do is, so this dashed line, I said it is my original message signal, right? And this is my staircase is the approximation signal, right? So to begin with, so I take this as a TS. Okay, sample, I am sampling it TS, 2 TS, 3 TS and so on. Okay, but I think so first one is TS. I hope you will be able to understand. Next is 2 TS. This point is 2 TS. The next point is 3 TS. Okay, 4 TS and so on. So here I will be comparing this staircase approximated signal with my incoming signal. Okay, so at first TS, my staircase means at this point of time, my approximated signal, staircase approximated signal is greater than the analog input signal. So it will be decremented by delta. Okay, where delta is the step size. Okay, so here it will be decremented by delta. Then for the next TS, means next TS, again it will be compared with my analog input signal. Even at this point also, my this staircase approximated signal is still greater than my analog input signal. So again it will be decremented by delta. Okay, so next for this is 2 TS. Okay, this point is 2 TS. Next is 3 TS. Okay, so it will be there in that level only. So at this point of time, what is now happening? The staircase approximated signal is less than the analog signal, right? So now it will be incremented by delta. Now it will be incremented by delta. So again for next TS, till the TS it will be constant only. Okay, I think this is TS, 2 TS, then 3 TS at 4 TS. So at this point of time it will compare. Now the staircase approximated signal is greater than my analog input signal. So it will be decremented by delta. Okay, and it will be there at that point only till the next sampling duration. So now again at this point it will compare. Now the staircase approximated signal will be less than the analog input signal, so it will be incremented by delta. Hope you are understanding what I am saying. Hello?
Sir, can you repeat it, sir?
Yeah, I will repeat once again. So here, so yeah, this dashed line is my analog input signal. Okay, I need to convert this analog input signal into equivalent digital signal. Okay, zeros and ones. So how do I do that is, first I do the approximation. Okay, I will come to that. How do I do that approximation and all? So for example, so this staircase is the approximated signal of this analog signal. Okay, so I start sampling at the TS, 2 TS, 3 TS, 4 TS and so on. Okay, so to understand, to begin with this, so I will be sampling at say 0 to TS. Okay, at this point of time, that is a TS, right? So at this point of time, my approximated signal will be greater than the original analog input signal. Okay. So now what I will do, I will be decrementing this by delta. Okay. So where delta is the step size. Then for next sampling interval, that is for 2TS, at this point of time I will be comparing. Now also my approximated signal will be still greater than the analog input signal. So further it will be decremented by delta. Okay. Till next TS it will be that value only. So this is at TS, this is at 2TS, this is at 3TS. At 3TS, now my approximated signal is less than the analog input signal. Okay, now it will be incremented by delta. Okay, so here either I can increment by delta or it will be decremented by delta. Only two values will be there. Okay, plus delta or minus delta, where delta is the step size. Okay, so at this point of time I incremented by delta, right? So it will be there that value only till further next sampling interval. So at this point of time, okay, at this point of time means this is first TS, no? Then 2TS, 3TS, then 4TS. At 4TS, what happens? The approximated signal is greater than the analog input signal. So now it will be decremented by delta. Okay, fine, and it will be there that value till the next sampling interval. So now again it will compare. Okay, so this is what TS, 2TS, 3TS, 4TS. At 5TS, now the approximated signal is less than the analog input signal. So now it will be incremented by delta. Okay, then it will be there that value till the next sampling interval. So now again it will compare with analog input signal. Now the approximated signal is still less than the analog input signal. So it will be further incremented by delta. Okay, so it will be there that value till the next sampling interval. Now at this point of time also, the approximated signal is still less than my analog input signal. Hence it will be incremented by delta. Okay, so till next sampling interval. So at this point also, my approximated signal is less than analog input signal. So again it will be incremented by delta. Okay, so till next sampling interval it will have that value. At this point of time also, the approximated signal is still less than my original analog input signal. Hence it will be incremented by delta. Okay, so now it will be there that value till the next sampling interval. So at this point of time, my approximated signal is greater than my analog input signal. Hence it will be decremented by delta. Okay, it will be there that value till the next sampling interval. Now the approximated signal is less than my original analog input signal. Hence it will be incremented by delta. Okay, it will be there that value only till the next sampling interval. So now what is there at this point of time? The approximated signal is greater than the analog input signal. Hence it will be decremented by delta. Okay, so it will be there that value till the next sampling interval. At this point of time also, the approximated signal, right, will be what? Is it greater than or less than analog input signal? It is greater than analog input signal, no? So it will be decremented by delta, right? Till the next sampling value that will be there. Here also it is greater than analog input signal. It will be decremented by delta. So like that it keeps moving. Okay, at this point of time also, the approximated signal is less than the analog input signal. Hence it will be decremented by delta. Again, that value will be there till the next sampling interval. At this point of time also, the approximated signal is greater than the analog input signal. So it is decremented by delta. Okay, that value will be there till the next sampling interval. So like this, what I am finding is, so the approximated signal will be able to track my original analog input signal, right? Hope you understood this point, when it will be incremented and when it will be decremented by delta. Yes, you people should say when it will be incremented and when it will be decremented by delta. Is that point is clear? Whenever the approximated signal is greater than the analog input signal, okay, it will be decremented by delta. Whenever the approximated signal is less than the analog input signal, then it will be incremented by delta. Hope at this point is decremented by delta, at this point also decremented by delta, but at this point it will be incremented by delta. Okay, Again, at this point, it will be decremented by delta. So if that thing is clear, then understanding about delta modulation is clear. When it will be incremented and when it will be decremented. I said it will be incremented by delta whenever the approximated signal is less than the analog input signal. Okay. So whenever the approximated signal is greater than the analog input signal, then it will be decremented by delta. So here only I have two cases, plus delta or minus delta. So when it is decremented by delta, I denote it by 0. Okay, so first two cases decremented by delta, that is why I am representing two zeros. Right? So next case it is incremented by delta, I am denoting it by 1. So next case again it is decremented by delta, I am denoting it by 0. So incremental value of delta will be represented by binary 1. When I decrease by delta, that will be represented by 0. Hence, I will be able to get the binary sequence zeros and ones. So which is approximately equal to my original analog input signal. Yes, if you have any doubts, you can ask me with this. If you want, I can repeat once again. Only two things are there. See, analog input signal. Okay, that analog input signal is what? That is my staircase waveform. Okay. Not staircase. Analog input signal is the dashed version of my dashed version. Okay. We'll be able to see. Dashed version is there, right? Dashed version is the analog input signal. And this is staircase version. Staircase, this one is the approximated signal. Okay. So here there is a block diagram. I will come back to that this block diagram. So first, with respect to this figure, you should be able to understand. So to begin with, what I said, the approximated signal. Okay, at this point, if I take, this is my sampling duration, I compare the approximated signal with my analog input signal. Here, the approximated signal I said is greater than the analog input signal. Hence, it will be decremented by delta. Okay, and it will be there that value till the next sampling interval I said. Okay, so this is a 2 TS. At 2 TS, again I compare with my analog signal. Here also, the approximated signal is greater than the analog input signal. Hence, it will be again further decremented by delta. Okay, so that value will be there till the next sampling interval. That is at 3 TS. Now, the approximated signal is less than the analog input signal. Okay, hence it will be incremented by delta. Okay, and it will be there that value till the next sample value. So at this point of time, right now, the approximated signal is greater than the analog input signal. Hence, it will be decremented by delta. Okay, and that value will be there till the next sampling interval. Again, at this point of time, the approximated signal is less than analog input signal. Hence, it will be incremented by delta. Hope this point is clear. So when it will be incremented by delta, when it will be decremented by delta. If you understand that, then you will be able to write the explanation of this delta modulation. So whenever we do the decrement by delta, that will be represented by a binary value of 0. Okay. Whenever we increment by delta, that will be represented by a binary bit 1. So in that way, I get only two values, either 0 or 1, 0 or 1, 0 or 1. Okay. So instead of in PCM, means here only two quantization levels, either 0 or 1. Hence, it is called 1-bit quantizer. Okay. So two quantization levels I can represent with what? 1 bit, either 0 or 1, right? So with that, I will be able to reduce the bandwidth requirement for transmitting the message signal. I will come back to these equations with respect to this block diagram. Hope this concept is clear. Yes, dear students, have you understood? Hello?
Yes, sir.
It is very simple to understand if you are attentive. If you miss, okay, at the beginning, how do I get this approximated signal? I will come back to that. For understanding, I said, let me take from this point, it is at 0, right, sampling. So at TS, I have taken here, right? This is my approximated signal value. I started comparing the approximated signal with my input signal. Since approximated signal is greater than the input signal, analog input, right? My analog input signal. So the value will be decremented by delta, I said, right? That value will be there till the next sampling interval. Okay, till this value. Again, I compare that value with my analog input signal. Since here also it is greater than analog input signal, so I will be decrementing further by delta. So that value will be there till the next sample interval. So now I compare this approximated signal with analog input signal. Now my approximated signal is less than the analog input signal. Hence, it will be incremented by delta. Okay, so it will be there that value till the next sampling interval. So now again I compare. So every TS I will be comparing the approximated signal with my analog input signal, and I take a decision whether it should be incremented by delta or decremented by delta, depending upon whether the approximated signal is greater than the analog input signal or less than the input signal. Okay. Yes, is that fine? Yes, I'm asking, is that fine? Hello? Hello?
Yes, sir.
Okay, I think with this I will stop for today. I will continue next class. Already it is. So all of you write your USN in the chat box.